Our third property of waves is diffraction. When a wave, for instance this wave coming this way, whose wavefront is shown in blue and which is moving, for instance, like this, so we have nice rays going like in this direction, encounters something like a barrier, then part of the wave is going to get stopped on that barrier. And the question is, what's going to happen to the rest of this wave? And the answer is that wave will attempt to bend around the barrier. And how this happens is that the barrier begins to create, as the wave bounces into it, new waves that will add up by the method of interference that we'll talk about in a minute. So the net effect is that this wave will not just completely go straight along with this middle piece cut out, but in fact it will slightly be diffracted. And so what you get is kind of a wave that looks almost like it did before, except that it will slightly spread out. And the same thing down from here. So if we go far enough, it's possible that a wave can strike here even though that part of the wave would have been blocked. In other words, it's bent around this barrier. And we'll draw the rays perpendicular at different parts of the wave. So there's still the regular wave, but the wave has now started to no longer move in a plane but kind of spread out. This is most noticeable when you have what's called an aperture. That is, you have a barrier with a small opening. An example of that might be light coming through a window. Now in the case of light, light's wavelength is less than 1/2 millionth of a meter, and the size of the aperture, that is this gap that's the window, is much larger. If that's the case, a lot of waves can get through the aperture, so the wavefront is not disturbed much, and the bending or diffraction is small. So if this was the opening here, we'll call this A for aperture. If that dimension A is much larger than the wavelength, small diffraction occurs. It's almost as if the wave travels with the law of inertia in a straight line at constant speed. So it's kind of like that the wave just continues like maybe you would have thought it would have. Mostly it's just the original wave, but there is some small spreading. So the wave largely just continues, and this part of the wave is simply eliminated. So it's almost as if the wave just continued like that. If you were sitting over here, let's say there's a person in, and they're trying to look at another person over here, you can't see them. That is, you can't look around the corner. And the reason is the light rays from them go in a straight line. The only way to see them is to get where the light strikes, that is, to get up here. This is the reason that you get a shadow, that is, there's an absence of light over here and here. This is the reason that you can't see around corners. It has to do with the short wavelength of light compared to the size, of, for instance, of the door. But if you think about it for a minute, you can hear someone down the hall even though you can't see them. So their sound waves have bent and gone through the door. This is because sound waves have a much longer wavelength. So if the aperture here, if A is less than or about equal to the wavelength, you have large diffraction. That is, you get a lot of bending. So what does this mean? This means that this wave goes into this small gap and it gets stuck. and then it becomes basically a point of spherical waves expanding out from that location. So it gets tied up in here and it starts spreading out. So you have waves going out like this. So your friend over here can yell, and even though you're sitting over here, this being the door, and you can't see them because the wavelength of light is so small it would have gone straight line, your sound wave is bent and you can hear them. This bending of the light, because, or any other wave like sound, because it goes through a small aperture or barrier, is called diffraction. So the next time you hear somebody yelling at you down the hall, remember, the only reason you can hear that is because of diffraction. And the reason you can't see them is also diffraction is not large enough because of the small wavelength of light. Now Newton did not know this, and Isaac Newton thought that light was a particle because he didn't think it diffracted. He didn't realize that it had such a small wavelength compared to things like windows and doors and various other apertures that you run into. This covers everything about diffraction.